Hi, everybody. Good afternoon. Thank you guys for being here so far. About 3 more minutes until 4 o'clock, and then I'll just start talking to you guys about the last few notes on chapter 12, and then we should be good to go for the weekend. Hi, Megan. Good to see you. Hey, Adriana. Good to see everybody there. Hey, Rose. And Fernanda, Sophia. Awesome. Good to see you guys. Hey, Jalissa. Hi, Pamela, or Pearl, I should say. How are you? Good to see you. Just gonna get myself a little soft drink. Okay, just hanging in there for another few moments. Hi, Nate. How's it going? All right. Well, it's pretty much 4 o'clock, so I'm just gonna get things going. Thanks again, everybody, for being here. As usual, feel free at any time if you'd like to send an email about the grade. When did you send it me? Let me know if you could, real fast. When you sent that one out? Was it today? Just a question. If you can give me a quick reply. You heard me? Maybe? Sent it out on Tuesday? Ah, okay. I'm going to get to it right after class then. I thought I cleared all my messages from Tuesday, but yours must have been left off from my replies. So don't worry. I'll get to you tonight. I have to teach until 6:45, but right after that I'll get to you. And then Tyler Doe, I know you might be here watching. We spoke earlier during the office hour. I'm still going to send you your message. I just had to get my notes prepared a little bit just before the meeting here. So not to worry. I'll definitely get back to you. Thanks, Nee. Anybody else that's ever looking on a reply or something that seemed to have been overlooked, just always feel free to bring it up in the meetings. I welcome that because I want to make sure I get to everyone's messages. Usually I do without fail. Once in a while, I suppose one can slip through because I am receiving hundreds and hundreds of messages all the time. So the first priority is to make sure I'm collecting all your assignments. And then sometimes with the grade checks, I guess they could get obscured in the volume of messages. But I'm trying my best. I think I have a pretty good track record with a few exceptions. Anyways, thanks, guys. Okay, so today the plan is to just finish up all the remaining material of Chapter 12. And then you guys will be prepared and ready to go for the quiz, the third quiz, which is next week, Tuesday. So you've had 2 quizzes before. One was on Chapter 8 and Chapter 1. Then the second quiz was all about Chapter 5 and the fallacies. And then you have just this one more quiz. Other than that, the last exam type of assignment is the final. So let's just finish off the remaining topics in Chapter 12. Okay, so it's still science for now. So the stuff we've so far talked about on chapter 12 was what is science? What are some of the important figures within the early history of Western science? What are some of the key assumptions that are found that are sort of built into science? We talked about what are some of the limitations that science has, things that it must assume to be true, or methodological constraints that it can't really quite prove. And then we also finished last meeting with a discussion of 4 different attitudes people could have about the relationship between science and religion. Some people think that science should predominate over religion if there's a disagreement between them. Other people think that religion should be preferred or prioritized if there's a disagreement between the 2 realms. Some people think that they're actually not even dealing with the same material, that they have separate subjects and therefore they don't have conflict. And others have a 4th possible view, which is that they are really compatible. And if you interpret religious scripture the right way, we would actually say the same thing as the scientist. Perhaps just got to work through the interpretation a little. So those are things we covered last time, which brings us to the next part of chapter 12, all about the scientific method. So we're now going to just discuss the steps of the scientific method. Different textbooks will sometimes divide these steps up a little differently. Our book is going with 5 steps. Okay, so we're going to deal with 5 steps, the steps of the scientific method. Okay, so first of all, the first step, the initial step, is simply to identify a problem. So that's number 1, identifying a problem. And what we mean by that statement is, you observe the world and you identify some unexplained phenomenon. You're trying to look at something in the world that happened, but you don't know exactly why or how it happened, at least not yet. And then that's the task of the scientist, to give us the explanation. So if you don't have some unexplained thing, then science has nothing to do. Science is the business of giving explanations, cause-effect explanations for the why of, or the how of how things happen, or the why of why things happen. But we have to have some kind of problem to explain to get the process started. So that's the first step. Observe the world and identify Okay, so there's a lot of different things that could be the case of this unexplained phenomenon. One example given in the book is, so right now in the world, there seems to be a rapid decline in the overall number of bees. The term used to refer to that is the bee colony collapse disorder. So, people who study this issue have noticed that if you just look at a graph, you'll see that the aggregate number of bees has been significantly declining over the past generation, 20 years or so. And that's something that's happening. And so you could argue, you could ask, why? Why is it happening? Why are the bees going down in numbers? That's mentioned in the book as just one example of something that could be this initial first step. Notice that at the first step, you're not saying, here's why it's happening, and let me tell you exactly why I think it's happening. You're just pointing out that there's some event, some phenomenon, and so far, we don't exactly know the reasons why it's happening. Okay, so that's one possible case. We can imagine almost infinitely many others. If this was the time before we understood how eclipses worked, then you can imagine people in earlier periods of human history looking up in the sky, seeing that the sun has been blocked temporarily during its normal hours when it would shine, and being like, okay, darkness has been cast around during the daytime. Well, that's something that has happened, but I don't know why. And now it's the job of the scientist, the researcher, to try and figure out why. So there's a lot of things that we can study scientifically, but we have to first of all have some kind of problem that we need to investigate. So let me see if there's more I can read from the book on this. Scientific method begins with the identification of a problem for investigation. This requires good observation skills, a curious mind, and the ability to ask the right questions. They give this case. Biologist Russell Hill, studying athletes on British soccer teams, observed that the teams that were wearing red seemed to win more often, and he asked, could there be some kind of cause-effect relationship, like wearing red has a tendency to enhance the performance of the athlete? You know, whenever there's something that we don't yet understand, science can take that as its task to try and give the explanation. So we identify a problem, some unexplained phenomenon. That's step one. Okay, moving on then to the second step. The second step of the scientific method is one of the major important steps, and that is to develop an initial hypothesis, okay? Okay, so when we develop an initial hypothesis, we give an educated scientific guess to try and explain why the problem occurs that we identified at step one. Okay, so a hypothesis, the word hypothesis just refers to an educated scientific guess that explains why something happens. It's a hypothetical thesis. So it's your reasoned judgment as to what the cause could be, what the explanation could be for the phenomenon that you first identified. But we say that it is an educated scientific guess because it's not yet been proven. You're just sort of making an informed speculation about the cause, but this has to yet be tested. So at this level, at the second stage, we haven't tested the hypothesis, but we formulate and develop one. So going into the example I mentioned about the bee colony collapse disorder, in fact, I could say more about that. The textbook mentions bees, but in scientific literature I've read over the past few years, the problem seems to even be more widespread, covering other insects. So there generally seems to be a large scale dying off of many different insect species, but we'll focus on the bees for now. Bees seem to be declining. Okay, well, what could be a reason? So when we start thinking about how could that be happening, why, now we're trying to do step two. Maybe one person thinks, is it because it's somewhat correlated with the rise of cell phone technology over the past 20 years? You know, that has definitely proliferated and expanded a lot. Maybe the 4G or 5G cell phone tower radiation that is out there is interfering with the life cycle or the migratory or the mating patterns of these bees. Could that be the explanation? I don't know. Could it be changed weather conditions due to the side effects of global warming? Well, whatever we think could be the explanation, we try to give some explanation, and now we have an initial hypothesis. Okay, so I'm going to go ahead and move on to the third step. So at the third step, the textbook provides this third step, which they call gathering additional info and refining the hypothesis. Okay. Okay, so this step just means that sometimes as you start to collect your initial data after you've given a hypothesis, you might notice that the hypothesis has to be narrowed down, made a little more specific, tweaked just slightly. Okay, so based on your initial data collection, you modify the hypothesis if necessary. Okay, so gather additional info and refine the hypothesis. Let me give you an example. So one thing that's been remarked on some in the media, and I think it's perhaps just well known in general by the public, but there seems to have been over the past 10 years or so a sad kind of increase in the rates of depression and suicide in young people. So for whatever reason, that seems to be something that is happening more now than perhaps 20 years ago. So that's a problem, right? That we could just say we've identified like greater rates of suicide in young people than, let's say, 20 years ago. Okay, well, that's something that's happening. That's step one, just identifying that it's happening. Step two, okay, so suppose someone has this hypothesis. They think, could it be that over this last 20-year period with the rise of social media, something about social media and social media engagement, because we know that like over 94% of people that are college freshmen are on some type of social media site. Could this somehow lead to greater rates of, youth depression, suicide, and all of that? That could be a hypothesis, But suppose that as a person starts to collect their initial data to study this question, they notice that the greater rates of depression and suicide are not just on all social media sites or users of all sites, but more in the case where they are the photo sharing sites, like, I don't know, Instagram or like short video sharing sites like TikTok. Could it be that it's only some kinds of social media sites and the engagement with those? And could it also have to do with a certain number of hours, right? So as we start to narrow the hypothesis down, we started off with social media is causing more people to basically commit suicide. But then you could look at the initial data and start to refine it and make it a little more precise of a thesis. Like, okay, well, some kinds of social media sites, the ones that specialize in these types of content, and maybe only people who engage in certain amount of time or, within certain types of demographic or whatever, okay? So there's many cases in which a thesis could be refined. I can imagine, since we're talking about social media and current trends, there's been a lot more of the mass shootings over the past 20 years too. I remember when I was in high school, way long time ago, there was the, Columbine case in Colorado. That was one of the early ones that gained a lot of national attention in 1999. And that was like a shock because we weren't used to really having school shootings back then. And then, by the time we reached now 2020, it sort of had become more normal, not just at schools, but all kinds of other public places, malls, movie theaters, you name it. Just kind of scary the way people using these weapons. But that's an epidemic in a way that had happened, and that's a problem. So someone might have had a theory. What could be the cause? Maybe someone, and I heard people give this theory, which I don't agree with at all, that, it had to do with certain types of video games. And then maybe the person, is doing their initial fact finding and they say, it doesn't seem to be any kind of video games like, Pokemon or like, Animal Crossing, but maybe first person shooter games. You see a pattern in the profile of people who've done such acts, having had played such games maybe reliably in the past. So what started off as a thesis that it's video games that are contributing to the rise of such shootings, the person narrows it to a certain genre of video games. By the way, though, I'm just giving that as an example because I don't personally believe that it has much to do with playing video games of any kind. And I love all those first-person shooter games myself. But if I was to give my own theory, I'd have to say it has more to do with the culture of guns that we have and the access to the weapons in our country, because these games are being played everywhere, around the world, Japan, Europe, and they don't seem to have the same issues with the, mass shootings. Anyway, so just giving you examples, right, to think about a way of applying step 3. Jasmine, does there always have to be a prior research to develop a hypothesis, or is it usually during this third step of gathering information that any research is done? Well, I say it's an educated scientific guess when you give your thesis, your hypothesis. So there's going to be some level of review of research and inquiry before you provide the hypothesis. But it's not going to be like the most thoroughgoing investigation of whether that's the correct hypothesis yet, because that's when you test it later. But yeah, there's going to be at least a minimum of prior research. You couldn't just toss out a really random theory with no even, I guess, appearance of being rational explanation for the problem. But you can be, I think, a little bit more lax in the level of intensity towards your research in the beginning, because the initial hypotheses, you're willing to allow them to be falsified by testing. So you're not necessarily waiting and waiting and waiting until you have a perfect research to supply a hypothesis. But you also wouldn't just throw it out there without having any understanding of the facts surrounding the topic that you're trying to study. So it's kind of like something in the middle, I guess, Jasmine. There will probably be some level of prior research before you develop a hypothesis, but much of the work of verifying these hypotheses comes out in additional steps that we're going to talk about just now, like doing the test, basically. Okay, so that's step 3. Now let's go to step 4. The 4th step is, I think, it's perhaps one of the most important, if not the most important, because this is when you put your hypothesis to the test. So you test the hypothesis. Okay, so after you've done all your observations and you've collected data, you refined your hypothesis however necessary, now you're ready to go ahead and test it. So basically now you conduct an experiment which will either confirm or disconfirm the hypothesis. Now, the experiment that you do can be done in either the real-world setting or in a laboratory setting. So conduct an experiment in either a laboratory or real-world setting. Conduct an experiment in either a laboratory or real-world setting. The experiment will either confirm or disconfirm the hypothesis. Okay, so now you're going to do this experiment, and the experiment is going to have one of 2 outcomes, either confirmation or disconfirmation. All right, so let's work again with that example I mentioned of the bee colony collapse phenomenon. Suppose that the theory that one had is that these bees are dying because of exposure to cell phone tower radiation. Now, if that's the theory, right, or I should say hypothesis first. It's a hypothesis before it becomes a theory. So we'll talk about that in a minute. But that's your hypothesis, that it has to do with the cell phones. So if that was your hypothesis, how could this be tested? Well, you could get 2 different groups, right, of bees. One bee colony you could place in an environment where you control for the fact that they're going to be exposed to high amounts of this type of cell phone radiation. And then another bee colony to compare it with is not going to be exposed to that type of radiation at all and basically prevented from exposure to it. Okay, so you have these 2 colonies. One has been exposed to a dependent variable, the cell phone tower radiation. Now, what would be confirmation of the hypothesis here, according to this experiment? What would be the result of the experiment that would give someone evidence that they actually did have the right hypothesis or the right explanation? If what happened after that experiment? If you could just sort of tell me that. What's the result that would be successful confirmation in terms of this bee colony collapse being caused by cell phone tower radiation? You heard about the possible test setup and design, the materials used, and the way the test would work. So what would be the result that would show that maybe you did have the right explanation, and it is, in fact, perhaps these cell phones? What would be the result that would demonstrate that? Let me know here in this chat. Okay, Jasmine, if only the bees exposed to the cell phone tower radiation started dying out, while the control bees were unaffected. Correct. So, if you've identified the right factor that causes this thing to happen, then what you should see is the predicted effect of the hypothesis, that the bees exposed to them in sufficient amounts are starting to die off in a way predicted by the hypothesis. Now, what would be disconfirmation? Someone could tell me that. Since we now have heard what confirmation of the hypothesis would be, this should be easy. What would be disconfirmation, though, of the same hypothesis and with the same experiment? What result would show that this wasn't the right explanation? Easy enough to say, but you should tell me. So, right. Well, if both die out, that would kind of be complicated because I guess it would mean that there's no effect either way. But I think more in terms of the second disjunct there in your statement, that if neither were affected, or if the cell phone tower radiation exposure group shows no measurable decline in number and it has no bearing on their life cycle as compared with the other group, then it looks like this is actually a factor that makes no difference to how well they survive or don't survive. So that would not be confirmation for you. Okay. Now, if your hypothesis is confirmed by the test, good. Then you've gained confirmation and you can basically publish the results, and other scientists and other researchers will go ahead, look at the results, and try and replicate them in their own studies. And as they continue to replicate and reconfirm the results, then your hypothesis is gaining more credibility and it's on its way to being regarded as a true hypothesis, like a theory. On the other hand, maybe your experiment didn't confirm the hypothesis, which is possible. Not every hypothesis is correct, and if it's not, the test will show us that. But if the hypothesis is not confirmed, then what step do you think you will return to in the process? If you get disconfirmation, you got to go back in the steps, but to what number? What do you think that would be? So, you tried to check for the cell phone thing, it didn't do anything to the bees. Now, you got to return to which step of the process until you can tell. You go back where? To which number? Yes, step number 2, you'd create a new hypothesis, right? Because the problem is still there. It still has not been explained. One hypothesis was not the correct explanation. The test shows us that because it didn't confirm it. So now you go back to step 2, try and come up with a different hypothesis, and run through the steps again until eventually you have an experimental result that confirms this hypothesis. And in that case, you're on the way towards getting the right explanation. So that's just a discussion of the 5th step, actually. So let me write it down here. The 5th and final step of the whole process is when you you evaluate the hypothesis based on the test results. Okay, so that's step 5. Okay, so basically at this point, if the results of the experiment confirm the hypothesis, there are 2 possible outcomes. If the test results confirm the hypothesis, then in that case, publish the results, and the scientific community will try to replicate those results. So for further replication, so then publish those results for others to replicate. But if the test results do not confirm the hypothesis, or disconfirm, as you could say, if they don't confirm the hypothesis, then in that case, go back to step 2 and repeat until you get confirmation with some hypothesis. All right, so that is the, I guess, written version of what we just now talked about. Let me read it then in the book, see if I can give you a little more context from the book. The last step in the scientific method is to evaluate the hypothesis using testing and experimentation. If the results or findings don't support the hypothesis, scientist rejects it and goes back to step 2, come up with a new hypothesis, and repeat the process. So yeah, the scientific method is ongoing. Old hypotheses and theories may be revised or discarded in light of new evidence, or replaced by hypotheses with greater explanation power. After 4 years of research into the cause of honeybee colony collapse, a 2010 study at Penn State College of Agriculture found unprecedented levels of particular pesticide chemical in honeybee pollen in hives. However, this hypothesis, while one of the most promising, has yet to be proven. The current hypothesis has been expanded to include multiple causes, including new and emerging pathogens, bee pests, environmental and nutritional stresses, and pesticides. So anyway, yeah, a little bit of contact with the textbook. So there's a little bit more in chapter 12 from here. After that, there's some discussion of how the steps in the scientific method are somewhat comparable to the steps in the critical thinking process. So let me go over that. Okay, so the steps in the scientific method have significant similarities to the overall process of critical thinking itself that we've discussed earlier in the semester. Now, I'm going to simplify a little bit the steps, just breaking them down into the big three. So the steps in the science method go from observation of a problem. Then from there, it moves on to creating a hypothesis to explain the occurrence of the so-called problem. And then after that, we get to the ultimate step where we do an experiment to test whether that is the right hypothesis or not. Now, this is, again, I'm saying a little bit of a simplification because it's omitting, refine hypothesis and evaluate based on test results, the hypothesis. But anyway, 3 steps. Now, maybe someone remembers basically what are the 3 steps of the critical thinking process. There are 3 steps there too, at least according to the book. And who could tell me that? It goes from blank to finally the 3rd step, blank. So what are those steps in critical thinking? Just let me know, and then I can put it on the board. It's somewhere in your mind or in your notes. I know it's in the book, but let's see who can get it out there. You start critical thinking by just, well, let me know. I don't want to make it too easy. I just want you to tell me. It's way back. It's in chapter 1, but it's a fundamental thing, so it's not to be forgotten. Not today, not ever. You need to remember it. So just let me know. What are those steps in the critical thinking process? There's definitely some steps. Just let me know what they are. Okay, good, Megan. You've got experience, interpretation, and then analysis. That's right. So, in a way, those 3 steps remind us of these steps a bit. So let me just put that here. First, there is to experience something. And when you're doing critical thinking, you don't want to just stop there and say, hey, something happened. You want to think about why, though. Why did it happen? What's the explanation? And that's when you get to an interpretation of why. But as a critical thinker, you don't even leave it at that. You have an interpretation, but you say to yourself later, is that the right interpretation? Is it correct or is it not? Maybe I need to reconsider it, or maybe, it is correct, but you have to think about it twice. That's because that's when you get to the 3rd step, which we call analysis. Okay? So with critical thinking, it's very much like science, just in an everyday context. You start off with things happening, and you're like, why? That's the same thing that a scientist does. They see facts in the universe or in the world, and they're now interested in this question, why is that happening, and what's the reason? So the scientist goes from there to create a hypothesis, which is an initial attempt to explain why that thing happened. And that's like how we interpret our own experiences. Trump appears to have lost the election. Let's just say that's something that has happened. Well, what's the reason? People could give all kinds of, informed reasons as to why. Maybe it has to do with dissatisfaction managing the coronavirus pandemic. Maybe people have upset at the perception of racial inequity or something in our country. Maybe it has to do with the voter turnout operation or the availability of mail-in ballots. There's a lot of different possible explanations, but someone might interpret and give one. But then later, someone goes back to their interpretation and thinks about it again. They question, was that the right explanation? Is there something better I could give in terms of explaining it the right way? that's sort of how the experiment goes, because the experiment puts the hypothesis to the test. The experiment is used to determine if we should keep this hypothesis or reject it in favor of a different one. So I'm just expressing there that how there are some overall, generic similarities between the two intellectual processes. And it's mentioned in the book too. So they say this: the scientific method involves the identification of a problem and rigorous systematic application of observation and experiment in testing an explanation for the problem. As such, it is similar to the three levels of thinking: experience, interpretation, and analysis that we studied in chapter 1. Alone, experience or sense data tell us nothing. They have to be interpreted in light of our existing knowledge and theories. Like the three levels of critical thinking, the scientific method is dynamic and recursive, not linear, with analysis returning to observation to check for consistency, and interpretation being revised in light of further analysis and observation. The scientific method includes specific steps to guide a scientist through this process of systematically analyzing their observations. Although there is some variation in the steps between different scientific disciplines, the steps are basically identify a problem, develop a hypothesis, refine the hypothesis, test it, and then evaluate the results of the experiment to either gain confirmation or disconfirmation. Okay, so that's a quick discussion of those comparisons. So now, the next thing discussed on chapter 12 is, well, what are some qualities of a good scientific theory or hypothesis? And just one thing to mention really fast in passing is that what is a theory? Well, a theory is just a very well-established hypothesis, a well-proven, time-tested hypothesis. So theories start off as hypotheses, and then when they've been proven and replicated and reduplicated a lot, then they kind of graduate to attain the status of theory. A theory is also something that we don't say is absolute truth and can never be challenged. Even theories with a high degree of proof are still, at least possibly, incorrect, and that's something that science always holds as an open possibility. But a theory is like the closest approach to truth that we think science can make. Once we have theories, we think that they are, in fact, the right explanation. So a theory is just a very well proven hypothesis. Okay, so just wanted to give you that definition real fast, but I'm going to clear the board anyway now, and we are going to talk about, well, what are qualities of a good scientific theory or hypothesis? Because I guess basically they're not all created equal. Some hypotheses are better than others, and by noting what these criteria are, you'll be able to distinguish between the good hypotheses and those that are not so good. Okay, so qualities of good scientific hypothesis or theory. Okay, so first of all, there's relevance. Relevance to the problem being studied. Okay, so one thing that would disqualify a hypothesis right away is if it was not even related to the thing that it's trying to explain. And sometimes people do just have weird views. You know, they state some hypothesis, some explanation of something, but the explanation they're giving isn't even on the same topic as the thing they're trying to explain with it. So, you know, like we've had a lot of hurricanes, more hurricanes and more intense hurricane season in the past 15 years than there were in the previous generations before that. So, you know, what if someone had this hypothesis? Okay, well, looking at 2005 to 2020, there's been a lot more hurricanes. Also, the divorce rate has significantly increased over that span of time. You know, it's like 50% or more of people who get married will eventually get divorced in America. So maybe that's the reason. More intense hurricanes, and it's happening because there's more divorces occurring. But these two things are totally unrelated. You know, one is a social fact about people making up and breaking up. The other has to do with weather patterns and, you know, the condition of meteorology on the planet. So that would not be a viable hypothesis. It has nothing to do with the thing. So, you know, you've got to at least check on that. There has to be ballpark contact of relevance to the thing that you're trying to explain. Okay, now next up, Another quality of a good scientific hypothesis or theory is that it should be consistent with well-established theories. Okay, so let me explain that. A good scientific hypothesis or theory should fit in with all the other well-proven theories that have come before. It's not supposed to contradict the well-proven theories, okay? Because science is basically a body of knowledge that's supposed to build on the prior results of previous generations. There's a saying in science that when there's new results, that they're not completely new because you're standing on the shoulders of giants, right? So Einstein developed the theory of relativity, but he was assisted by the findings of Newton generations before him. And so he added to, expanded on, and made changes to certain of Newton's laws. Quantum physics takes some of the theory of relativity and goes further from there. And so like in science, basically, we don't want to have to just toss out everything with each new generation and start again. We think that we're building from the things that have been learned in the past. So a good scientific theory basically should be able to fit in like a puzzle piece to all the other stuff that has already been established before. If it doesn't, then it contradicts those theories, and that's not good. So a good scientific hypothesis or theory, a good theory will fit in and not contradict. Fit in with and not contradict other well-proven theories. Okay, so like, if somebody was trying to explain where their presents came from on Christmas, and they think this must have been Santa, that's my theory. Well, that theory is not so good, because if it was true, it would contradict so many other things that we've proven about physics, right? Like, because it would violate all these laws of it would violate all these physical laws, right? First of all, the claim of the Santa theory is that he's being carried around on a reindeer-driven sleigh that flies through the air, but we know that there's no mechanism by which the terrestrial land mammal reindeer could fly. Also, there's questions about how he could possibly carry that many items in one sleigh. So, it would violate all kinds of physical laws if this was true. It would violate our understanding of gravity, aerodynamics, biology. So to make way for one theory, we would have to reject so much other stuff that is totally well proven. That means it's not a good theory. A good theory fits in with and doesn't contradict the other things that have come already before. Now, there are very rare exceptions to this. There's like a revolutionary theory that has way better explanatory power. Then sometimes people say that can actually overturn something that has been well established in the past. So like I mentioned Newton's laws. In a way, those were rejected in a sense by some of the things that Einstein discovered. Because Einstein, one thing that's implied by his theory is that the fastest mode of information traveling through the universe is by means of light, which travels at a finite, very fast speed. In Newton's theory, when gravity acts on another object that's far away, it acts on it instantaneously. So there would be like no time delay between an object and then some other object that it exerts an influence on, or that it has some kind of gravitational force on. Well, I mean, not too much changes by our understanding of the universe when we see that Einstein's theory is correct, but it did invalidate at least some of those aspects of Newton's laws. So it's not impossible for a new theory to be good and accurate and to contradict things that have come before, but that's the exception, not the rule. It would take overwhelming experimental proof and explanatory power for us to have a revolutionary theory that just changes the whole paradigm. But, for the most part, it's a good thing when the theory fits in with others that have already been proven pretty well. Okay, so then we move to the next case of a quality of a good scientific theory. The next quality mentioned in the book is simplicity. And this concept that's being defined here, you'll sometimes see it referred to in other discussions, and in this book also on the side as Occam's razor. So just so that's also kind of another label that is used in reference to this concept, I'm putting it here. The simplicity concept is this. If you have two explanations, two different explanations for one fact, the simpler of the two explanations is the one that's likelier to be true. Okay, so that's a principle that science claims is really fundamental. The simpler of two explanations for some phenomenon is likelier to be true. Why is it also called Occam's razor? Okay, because there is this medieval philosopher, theologian, and scientist named William of Occam back in medieval England, and he first stated this principle, and so he kind of takes the namesake, and we still use his name on that today. But yeah, Occam's razor is just that idea that if you have two different competing explanations for something, which one's likelier to be true? The one that has a little bit more simplicity, that involves fewer assumptions. Okay, so it's a metaphysical assumption of science that the universe is elegant, parsimonious, which means that typically the simpler of two proposed explanations is the one that has a greater probability of being correct. Let me give you an example of this, perhaps. So suppose that you parked your car somewhere and then you went into, I don't know, a place like a campus or restaurant, whatever. You parked in some parking structure, left your car behind, did whatever you're doing. Now you're coming back to where your car was. So suppose you come back to where your car was parked, but it's kind of odd because it's not there. It's not in your parking spot, so your car's missing. Now, if that happened to you, you'd start thinking critically, I'm sure, and you'd start right away thinking, what's your hypothesis as to why? So let's hear a possible hypothesis that might be reasonable. An initial educated guess to explain why the car is not there. What could it be? If this has ever happened to anybody, then you can draw on personal experience. If it hasn't, I'm sure you can imagine that. What do you think would be a reasonable explanation? Okay, one thing you're saying, Jasmine, is you have the wrong parking spot. Okay. Aaron, you're throwing out maybe that it got towed. That's another possible reason to explain this, yes. So towing, maybe you didn't see some of signage that was posted and this is a restricted parking spot. Maybe the car's been stolen, that's another possibility. Okay, so let me just, because I got to narrow it down to just a few. So let me just give you the two, okay? Let's say on the one hand, the theory or hypothesis is that this car got towed away. And then suppose the alternative hypothesis is this other option. Maybe the extraterrestrial aliens came and abducted your car, right? So the aliens came down to planet Earth and they jacked your car. So here are two hypotheses: towed away, alien abduction. Now, I don't know, which of those do you think would be simpler? That would involve fewer assumptions. You don't have to assume as much for one of these to be true than the other. Which one is simpler and doesn't hold as many assumptions behind it? That it was towed away, yes. What are things that you have to assume to sustain the alien abduction hypothesis that you don't have to assume for the other one? You have to make all kinds of new assumptions. So if it's taken by aliens, first of all, we have to assume basically at a minimum that what? Like, what are some of the built-in assumptions to that hypothesis? Well, that the aliens exist, first of all, that they exist, and not just that they exist, but that they exist and that they are intelligent enough to build transportation from wherever their planet is to here, and that would be no easy task. I mean, we're pretty intelligent human beings, but to even get to the next closest star, we don't have any technology that can do that as of today. So these would have to be super intelligent aliens. They would have to have the means to access the planet Earth. They would also have to have some weird interest in your car, of all things. So these are a lot of very weighty assumptions. For you to go with that hypothesis, you have to assume so much more. That's not so simple and straightforward. So looking at these two hypotheses, one is the clear winner. One is much likelier to be true. And so that's how this principle of simplicity works. I think sometimes I can imagine other examples, like conspiracy theories, for example. Suppose that one person's, they see the archived footage of, Neil Armstrong and these guys walking on the moon, and one guy's hypothesis to explain the existence of the video is human beings built rockets and traveled to the moon and planted the US flag on the moon. Someone else has the hypothesis that that didn't happen at all, and that it's a big cover-up and that this is filmed in a TV studio or whatever. But for that to happen, right, we would have to make so many additional assumptions, like, for example, that everyone who works in the scientific community and NASA is in on this, that the photos and videos were all faked, you know, and so to sustain those hypotheses, you have to entertain all kinds of other assumptions that you don't have to for the simple, straightforward, credible hypothesis that this really happened. Maybe a better example could be the shape of the Earth. If you thought it was flat, contrary to the widespread consensus view of almost everybody, then you'd have to explain away the appearance of all the other planets and celestial objects, which are clearly spherical. You'd have to explain away the existence of photographs and videos taken by satellites and even from the lunar surface. And you'd have to sort of justify the claim that someone's out there to trick us about this because they don't want us to know that we're standing on a disk. These assumptions are not necessary at all to just hold the alternative that it's a sphere and that's what explains the appearance of it in photos. So anyways, Occam's razor directs us towards the simpler of two explanations as the likelier one to be true. So when you're trying to figure stuff out in life, going for the most complex, weird explanation is usually not the one that's correct. If there's an easier, simpler one that makes sense according to fewer explanations, then that's the likelier case to be true. And in the book here, it says about that, if rival hypotheses both satisfy basic criteria, scientists generally accept the one that is simpler, a principle known as Occam's razor, named for the medieval philosopher William Occam. The great majority of scientists reject intelligent design theory, so they're giving their own example of creationism versus evolution, because, among other reasons, the theory of evolution is simpler than that of intelligent design. Yeah, so if you assume creationism, you have to now also assume the additional existence of a supernatural being outside of nature who creates nature and the universe and everything in it. But to accept evolution theory, you don't have to presume that there's anything outside of nature and that the system just works according to its own laws. No need to add the idea of a divine being and to explain the mysterious relation that it could have to our universe on the evolution theory. Okay, so a couple more of these points, and then we'll be good. Another quality of a good scientific theory or hypothesis is what is called falsifiability. Okay, so falsifiability, it means that a good theory is able to be somehow proven to be false. Sorry for my definition here. Okay, falsifiability, the ability to be falsified, the ability to be proven false. Now, it might seem a little weird to you at first because you're like, wait, how can that be a good thing? If a theory is falsifiable, wasn't the whole point to prove that it's true? Yes, that is the case. But proving that a theory is true requires that there's some test that you could perform on the theory. And you can only test a hypothesis or a theory if you know what would count as disconfirmation of it, as what would count to be falsification of it. See, if you don't know how to falsify the hypothesis, then you also don't have any way of proving it either. Okay, so if there is no way, even in principle, to falsify a hypothesis, then it's not scientific because it can't be tested. Okay, going back to the thing about the bees. If you thought that it was cell phone radiation, well, that's a hypothesis that is falsifiable because you can put that hypothesis to the test. You can, create a controlled setting where you expose them to that variable, that factor, and if it doesn't have the predicted effect, I guess your hypothesis wasn't good, or, well, I shouldn't say wasn't good, but wasn't correct. But it's a good thing when we are able to perform the test. If we couldn't perform the test, then we could never confirm or disconfirm the hypothesis. So disconfirmation is a prerequisite to even being able to construct a test, okay? Like Einstein, for example, in the theory of relativity, he said, if my theory is correct, one of the implications of it is that when we have a solar eclipse, we should be able to see objects from the light that has been bent around the obscured surface of the sun. So like stars and such that are actually physically behind it should be visible from the planet Earth using telescopes, because the prediction of the theory is that the light is actually affected by the mass of the sun itself. So the light rays bend around its curved surface, and you can therefore actually see things that it physically blocks. He says, if my theory is correct, then the next time there's a solar eclipse, let's place telescopes to the sky and see if this phenomenon is seen. If it is, that's confirmation. If it's not seen, then that means my theory might be wrong. So a hypothesis in science is not just, hey, here's my theory, just take my word for it, and you can't do anything to disprove it. No. There has to be a way to disprove it in order for us to be able to gain confirmation also. So when it's not falsifiable, it's not scientific. And let me give you examples of things that are unfalsifiable. One, and this is mentioned in the book too, is some of the stuff that was discussed by Sigmund Freud. So Freud, as probably some people have heard, is considered by many to be like the father of modern psychoanalysis. And he did have some interesting discoveries, like the idea of the subconscious mind. But there's a lot of stuff that he wrote also that it doesn't seem to have any scientific backing, and that in the years since he lived has been widely discredited. Some of it thought of as like the drug-addled ravings of a person who did a lot of cocaine and all that. But he wrote, for example, weird stuff like that when you're a little boy or a little girl, that you have these latent sexual attraction to your opposite sex parents. So he thought that like the little boy develops what's called the Oedipus complex, and so they have a kind of latent sort of buried, sort of hidden internal desire for a woman that is in some respects similar to the mother figure, and this plays out in adult life by finding a woman that's similar to the mother. And in the case of the little girl, they say the little girl suffers from the Electra complex, which is the same thing but reversed. She has a latent sexual attraction to the father figure, and this leads towards the development of relationships in adult life with people that remind them of the father. They talked about penis envy and all kinds of other really weird stuff in Freud's writings. But the point is, the stuff that's not so well proven and that's unscientific, the problem is that it's not falsifiable. Okay, so suppose that you say to a Freudian, that's totally false, that's crazy. The thought that I would have had a sexual attraction, even if it's latent and subconscious towards my mother, that's not true, I didn't have that at all. What the Freudian would say is, you're just saying that because you've repressed these thoughts and they're deeply buried in your subconscious, so you can never really prove that this is false. That means that this is not a good theory, though. If it was a good theory, they would give us some mechanism by which we could prove it or disprove it. But if we don't have any possible scenario in which we could actually show that there's something disproven, then the person's making claims that can't be tested, and that's not actually scientific. That's more like speculative, just sort of suggestions. Okay, so good. And then in the book, here we see it. A hypothesis or explanation should be presented in a form that is testable and can be replicated by other scientists. In addition to being testable, an explanation must be able to be falsified. Philosopher Karl Popper pointed out that logically, no number of positive outcomes can confirm a theory, but a single counterexample does disprove it. Therefore, one of the main tasks of a scientist in testing the hypothesis is to search for falsifying instances. For example, if we have a hypothesis that all swans are white, just finding one that is not white would count to falsify that. And in fact, they did for a long time think that all swans were white until they found very rare black swans in Australia. But the discovery of that made it possible to falsify the generic theory that they're all white. So anyway, good scientific theories have a way to be proven false. Last thing about this. Falsifiability doesn't mean that the theory is false, though. It doesn't mean that it will be proven false. It just means that hypothetically, we know what kind of outcome would count as disconfirmation. But if we don't even know how to check for disconfirmation, then it's not falsifiable and not scientific. One more final example of these unfalsifiable claims that are not scientific would be like the horoscopes and the astrological signs. Now, I know some people believe in those things and they think they're fun and interesting, but I'm sorry to tell you that in this critical thinking class, there's no love, there's no respect for it at all. It's totally false, it's unscientific, there's no credibility or anything when it comes to these predictions. And one of the reasons that you know it's not scientific is because there is no way at all to falsify a horoscope. If you say, that thing didn't happen to me, the astrologer will just say, well, you weren't paying close enough attention to the events of your life, or you didn't interpret the zodiac sign message the correct way. So if it said, this week will be interesting because you'll be visited by an old friend, and you're like, I was on quarantine the whole weekend, I didn't see anybody, so how is that true? The astrologer won't concede that that's falsification. They'll say, well, maybe, a little bird perched on your balcony, and that's what it meant, that a little friend would visit you. You just didn't sort of think of it the right way. So it's now impossible to falsify, which means that it's not actually a credible scientific position. Okay, so much for falsifiability. From there, we just have one more of these qualities of a good scientific theory or hypothesis, and that's what's called predictive power. Okay, so predictive power is just a good scientific theory can be used to accurately predict future events. Okay, so one of the main reasons that science is so important and so valuable is because it gives us a sense of things that are going to happen in the future that haven't happened yet. If we understand how a scientific concept or law works, then we can use that knowledge and understanding to make very accurate predictions of the way that things will play out. Some basic, easy examples of this could be like, for example, meteorology, weather science, the science of weather. Now, the weatherman or woman, when they make the prediction and you read it in the news or you see it on your phone, it's not 100% accurate all the time, but it's also not just a random shot in the dark and it's just 50-50 whether the predictions are correct or not. For the most part, when the weather person says that it's going to have like a 75% chance of rain on Friday, it more or less bears out in the way that was predicted by the meteorologist. And so the fact that predictions issued by the meteorologist end up becoming true for the most part gives us a sense that these are not just people shrugging their shoulders like, I don't know, maybe that's how the weather will work, but that science of weather is correct, that it's getting to the facts and to the truth. If it wasn't, then its predictions would probably fail and usually come out to be incorrect, but they don't. So to the extent that a scientific hypothesis or theory gives us the ability to make realistic and accurate predictions of stuff, that adds further credibility to the whole scientific field that that's a part of. Another area could be astronomy, not astrology, but astronomy. That's physics and observation of planetary motions and the motions of other celestial bodies in space. Using that, we can actually determine with a high degree of precision when there's going to be another solar or a lunar eclipse. Maybe you guys have noticed that, but there'll be reports in the media leading up to the occurrence of an eclipse, even years in advance. Like even right now, if you wanted to, you could get online and you could find the exact time and date, right down to the hour of day, when there's going to be an eclipse. And you could also find out where on the surface of the Earth you would be positioned to best see it and see the full effect. Now, everyone knows when those things will happen, and that's why when the eclipse happens, nobody's surprised, because they've heard the reports in the media. So the great accuracy of such predictions and then the playing out of events in exactly the way predicted gives a reason to think that astronomy, meteorology, all kinds of other realms of physics, biology, chemistry, that they are true and that they're getting to facts about reality. So predictive power is another thing that gives a sense that this is a good scientific explanation. Okay, then finally, that's it for the qualities of a good scientific theory. The last thing in the chapter talks about the difference between science and pseudoscience. Okay, so we got to then quickly talk about this word. What is it? Pseudoscience. So pseudo just literally means false or fake. So if you kind of a crude oversimplification would be pseudoscience is fake science. But to give a little bit more of a thorough definition, this is a body of explanations that the text uses this terminology, so I'm going to borrow from it, It's a body of explanations that masquerades as science. Masquerades is perhaps an awkward term, but they're using a metaphor basically. To actually masquerade would be to put on like a mask to conceal your appearance or to make you look like somebody different. So metaphorically, pseudoscience is something that wants to appear on the surface to be scientific explanation, but it's actually just faking it, and it's just putting on a false appearance of being scientific. So it's a body of explanations that masquerades as science. Okay, so it's a body of explanations that masquerades as science, and there's many examples of this. So for examples to give, astrology, psychics, tarot cards, crystal balls, palm reading, we could keep going. But those are pseudoscientific. And the reason we would say this is because in every single case here, where there's like a pseudoscientific body of explanations, the claims they make are not falsifiable, okay? There's never any tests or experiments done to verify or to even try to disconfirm any of the claims that are made. So they're not falsifiable, they can't be tested, and they're oftentimes stated in vague and ambiguous language. They're using such vague language that almost anything could be claimed as confirmation for what they say. So like, take for example, it's one L, sorry there. Take for example, the prophetic writings of Nostradamus, which some people, place confidence and trust in. According to the belief of those, Nostradamus was this famous prophet guy who wrote a bunch of obscure writings that made predictions of all kinds of future world events, like 9/11, World War II, but that's not really true. If you go back to the original text and you read these things that are claimed to be predictions, they're stated in such vague and unclear language that you can almost say it predicted anything. Okay, so to the point that some say he predicted 9/11, this is the passage of writing that they think did that prediction. So Nostradamus wrote, way back hundreds of years ago, "And no fire of the center of the earth shall make an earthquake of the new city. Two great rocks shall long time war against each other, and after that they shall color red the fresh water." Okay, so did you get from that that there will be a 9/11 attack using airplanes on the Twin Towers in New York City from, international terrorist organization? It makes no connection. I mean, it would be the very, very faintest association. There's some talk of fire. There's some talk of an earthquake in a city and two rocks. But I mean, that could almost stand in as a so-called prediction of almost any global conflict involving two warring parties. And, the details matter. So obviously, if we take that to be an accurate prediction, we're going to be very gullible people. We could easily be manipulated, tricked, misled, giving our money away to things that don't benefit us, and so on. So be careful to distinguish between real science that does have the ability to be falsified, that provides language that we can actually use to test things. Distinguish that from pseudoscience, because some people are out there to try and make money off of you, to exploit you for their own advantage. And if you're gullible and easily credulous to the claims that people make, then you'll be the easy target for such con artists, frauds, manipulators, and all of that. Yeah, like read a horoscope, why don't you, and just cover up the name of which sign it is and tell me which one is yours. It's very hard to do that. It's not possible, really, because they're all so vague and ambiguous that almost anything could be counted as confirmation. So, well, we've covered a lot of good ground. We've talked all about Chapter 12 and stuff about science. So when it comes to our quiz on Tuesday, I just want you guys to remember the basic parts of Chapter 12 that we've covered. So I want you all to know about the definition of science. I want you to know a little bit about some of those famous historical figures, Copernicus and Francis Bacon. I want you to know about the different assumptions behind science that we talked about. For example, empiricism, objectivity, materialism, predictability, unity. Know about the limitations of science that were mentioned, the 4 attitudes that people could have about the relation of science to religion. Know about the steps in the scientific method and how there is some rough comparison between them and critical thinking steps. know what are the qualities of a good scientific hypothesis, and then also know what is pseudoscience and be able to give example of that. And that's all the stuff that you'd want to be ready to report on for the Tuesday quiz. And just as I've done before, I'll mail you the quiz at around our class time, and you will get about 90 minutes to do it. Which people specifically do we need to know about? Thank you, Aaron. I was saying Francis Bacon and Nicholas Copernicus. There's not too much specific mention. I mean, there's mention in passing of some other figures, but those are the historical figures I was most interested in for you to know about. Okay. Any other questions then? I guess if not, we'll probably be good to go for the weekend. I'll be in touch over the weekend as I'm working on your current homework. But other than that, you're just looking forward to the quiz for Tuesday. There's no other class meeting Tuesday. It won't be a lecture day. We'll resume lectures next Thursday with Chapter 9, and that'll be all about ethics, and that's our last chapter in the class before we turn our attention to the final. So is that all right, everybody? Are you good to go? Let me know. You can hit the like button or just say that we're good. And if you've got no other questions, then thanks. Okay, thank you, Megan, and to everybody else. Have a great weekend. I'll be in touch. If you need anything, do email me. So have a great one then, and see you next time. Bye-bye. Thanks, Ryan.